Hello YouTube viewers, welcome to my channel Science or Technology. In today's show, Future Friday, we're gonna talk about Breakthrough Starshot. So let's dive right into it. So what exactly we are talking about? First thing first, you have to understand this and you have to understand it very carefully. Interstellar travel, as in traveling between two star systems like our solar system and Alpha Centauri, flat out impossible at this moment in time. We do not have any technology in 2020 that can even allow us to comprehend that we may be able to do this. Flat out, zero, zilch, shunya, nothing. We do not have any technology for that. However, that being said, that's for human mission, but we can send probe. And given the fact that we did already have experience, like 40-year experience of Voyager probes, we know for a fact that electronical probes can work for a very long time. So we may be able to do that. However, another aspect is, while it is thoroughly accepted and kind of inevitable when you are talking about space mission, that you could launch a rocket and it's like, yeah, wait, how long you have to wait? Yeah, 10 years before it actually goes to Pluto and you get your mission. So that is expected, but still everything that we do, every mission that is planned, every mission that is launched has to be done inside a single lifetime, aka long enough where people can see that. You cannot tangibly expect someone to okay, invest billions of dollars and you may get this puppy in 700 years from now. People are like, no, no thank you, no thank you. So it has to be condensed inside one lifespan. That is necessary. So this is the main aim, and you have to truly understand this fact. Light speed, that is the fastest that you are possibly able to go in this universe, still takes years to go. Like at light speed, you are talking about freaking 4 years to go to Alpha Centauri. Like you have to go hundreds of times faster than light speed, where you can achieve what people have achieved in Star Wars and all that jazz. So flat out, this is what is the main aim of this mission. So which star we are talking about? We are talking about Alpha Centauri. Why? This is surprisingly close to us. That's the first thing. It's 4 light years plus to us. It's very close, surprisingly close given all the other data points. However, it's a very unique system. It's in 3-star system. Our star solar system is a single star. That's it. We have one sun. That's it. Go home. Done. There are many binary star systems. They have 2. Done. This puppy has 3. It has freaking 3 stars, man. Like 3. That's damn awesome. Like that's rare as hell. So not only that, the fact that it has 3 stars, it has 2 confirmed exoplanets, meaning we have, with all the certainty that we can get at this point in time, there is Proxima Centauri B and Proxima Centauri C. There are 2 planets already found with our current understanding and technology. So we are very interested in this system. Not only that, because you can understand this practically speaking. Like let's say there is a planet, exoplanet, we discovered it, we launched James Webb Telescope somewhere in 2000, 100 or something like that. We launched it, we found a planet is like TikTok copy of Earth, we have life signatures, everything is awesome. If it's let's say 200 light years, it's like okay. But this puppy, we got 2 planets. This is the closest that we can get. So humans did not directly jump to Mars. We first jumped to Moon, then we went all other places. So same thing will happen here. First we have to go to our closest star system, only then we can think about colonizing the galaxy. So this is very interesting. This is tantalizing enough where it's like, come on, you can do this, it's close enough. So that's why we are so focused on this star system. This mission is only made for this star system. Now how the heck the working works? One thing you have to understand, right now all this problem will be solved if we had a magical fuel, which we do not have. Flat out, you can take the biggest rocket human ever made, like let's say Saturn V. This puppy is huge, Statue of Liberty kind of huge. What is it? Basically fuel tank, nothing else. It's just fuel tank. So flat out, our fuel is the inherent limitation. We do not have any fuel that is like YOLO powerful. So we need at least 1,000 times more powerful than this, or 10,000 times powerful than this, to even come to a point where it's like, maybe I can do a mission to Alpha Centauri. So flat out, it cannot be done at this point in time. So somebody came up with the idea, if a rocket is like 99% fuel, how about we split those part up? So basically you put the fuel part on the ground where you don't have to carry it, and you just dump that energy into the payload. Done. That's all you are doing. That's what fuel is doing, is converting the chemical energy into kinetic energy into the craft. That's all it's happening. So the idea is use light sail. Now light sail have already been worked. It works as a physical thing. We have tested it in low Earth orbit, and we have tested it in a very deep space mission. It works flat out, known, tested science. However, our sun is not very bright, and not to mention it's not a laser. Like again, if you can focus all our sun's energy in one point and then fire at light sail, first light cell will disintegrate, but let's say you can bypass that, it will go at light speed. We don't have to worry about that. Sun has that, but it's not focused enough, so to say. So if you can make a laser system powerful enough and you fire it at a light sail, you can accelerate this puppy very fast, and you can get it good enough at light speeds. So that's the whole point. Ditch the fuel, like keep the fuel away, keep the craft away. Payload and fuel, they should be separated. Light craft is needed. Now you have to understand, if you have a very yellow powerful laser and you're firing at something, it will eventually end up accelerating that puppy to a maximum speed. Let's say that maximum speed is 20% of light speed. Yes, your mass does not matter at that point in time. If you do the calculation, you will always achieve that 20% light speed, no matter how big or heavy you are. Only difference would be, if you are light, you will achieve that in an hour. If it's big and heavy, you may have to fire that laser for weeks. And you can understand the fact that, given the fact we live on an earth which has a moving tectonic plate which is spinning, and then it's spinning around the sun, fundamentally you do not have a static place where I can fire a laser for very long enough time. So for that reason alone, we have to make a laser system that is powerful enough to push something very quickly, and the thing that we are pushing has to be light enough so it can be done in a small amount of time. We do not have any place where you can, like, okay, point that laser in that direction. If you look everything from top, let's say outside of celestial sphere, you will notice everything is moving. So you can understand, you cannot point a laser at something from a moving point, vantage point. So your time zone, your window of opportunity is very small. For that reason, the craft, the mathematics is out, and the mathematics is simple. You have to keep it light, as in less than a gram. Like 1 gram, 2 gram, you are going, forget about it, because at that point it will take almost 1 or 2 weeks to accelerate. So fundamentally you have to keep it inside a gram, maybe 2 gram, maybe 3 gram if you are acceptable with, like, yeah, it may not reach same light speed, not because of the laser limitation, simply because you will not be there. You spin out of your window of opportunity will move out. So fundamentally the craft, whatever we are making, the flies craft, everything, it has to be very light, and acceleration has to be done around an hour. That's the maximum every calculation is suggesting. It's like 1 hour you have to somehow accelerate this puppy from zero, like statically speaking, from 0 to 20% of light speed in less than an hour. So we got some serious hurdle to solve. Now what about the laser, this magical laser we are talking about? Now we have the laser that are powerful enough at this point in time. We are dealing with lasers that are like 100 gigawatts of power, 1000 petawatts of power. We got the laser, that's not an issue. But here's the deal, you may be like, wait a minute, we humans do not produce 100 gigawatts of power, we do not produce 1000 gigawatts of electricity. How the heck we are running these lasers? Well, we are not. What we are doing is basically charging this puppy up and dumping that energy in a small amount of time, because energy has two factors to it, like how much of energy is and how quickly you are getting. Think of it this way, 10 ampere. 10 ampere does not mean too much, but let's say 10 ampere in an hour, that's like power consumption of a iron cloth heater. 10 ampere in a second, whoa, now you're talking about some serious short circuit here. So same thing happens with laser also. So right now we have lasers that can cause fusion. Actual fusion can be caused in laser ignition facility. That's why it's called laser ignition facility. How the heck we are achieving it? We are charging this puppy up. So basically, let's say the power consumption is 10 megawatt. You're taking that 10 megawatt and you're shrinking it out. You're compressing that puppy. You're compressing that puppy to very narrow slit of time. Basically, you're going to 1 picosecond. At that point, it's like gigawatts of power, because again you have shrunk it. So we need that kind of power level. So we got the power level. That's just the power level. That's a spike. That's like camera flashes, like charges up the capacitor and go poof. We do not want that. We want continuous torch. That's the problem. Fundamentally we have to make a laser system that is multiple times, as in like multiple times more oomfish than this puppy, and somehow have the electrical bill to provide this energy to these puppies. So whole another level of laser system that we are talking, like this system will be so powerful, it will make a IC laser system that we deploy right now to shoot down ICBMs. It's like brah, those are cat lasers, those are for chump change. Like, this is man's laser. So fundamentally you are talking about a power level that we cannot comprehend. Another aspect, aiming system, because again we are on a moving thing, we are firing at a moving thing, everything is moving in this goddamn universe. So aiming system would be completely different and complex. On top of that, flat out mathematically, we do not have a system that can do that, except phase shift technology. Now, if you are familiar with the electronic industry in the recent times, phase shift is being said about everything. Wi-Fi 6 has a phase shifting technology. 5G has phase shift technology. What the hell that means? That simply means somebody figured out that we can have light has a property of waves, which means you can have cancelling wave and reinforcing wave. Basically, you can add to wave, reduce to wave. So benefit of that, mathematically you can build a single plane antenna. You can have a signal going like this, and you can mathematically switch it in such a way, like let's say you have hundreds of small antenna, you can switch it in that way. The signal goes whoop, You can do this. This is what we call phase shifting. So basically your physical antenna would be exactly the same place, but the signal will go wherever you want it to go. This is how 5G works. This is how radar system works. This is a known technology. It works absolutely true. Only difference is we generally do it for very large wavelength, like microwave, radio waves, that sort of thing. And we have to somehow do it with that exact spectrum which is needed for the light sail. So that has to be done. So first you will have an antenna that is like, being physically moved, then you will have electrically moving. Only then you may have the ability to aim a laser at a certain point, because these craft will be inside a gram. So you are talking about barely 1 meter square, barely, or maybe 10 meter square if you are making about some advanced nanotechnology we do not have yet. But again, it's not a very big target, so you need very high precision aiming system. Another aspect is, the most problematic aspect is, it has to go through the atmosphere. Atmosphere is made out of mixture, as in it has different gases in different quantities. Consequence of which is it's transparent to some wavelengths and opaque to other. If you use anything spectrum, basically laser spectrum is into the opaque department, flat out atmosphere will dissolve the energy. Basically you will end up heating the atmosphere rather than firing the laser, and it is a big deal. That's why laser weapons are not used in fighter jets. They could figure out even the energy source for a laser, but here's the moment they fire it, atmosphere is like, nope. It's like, firing a bullet in free air. Bullet goes very far. Firing a bullet inside a water, it does not go very far. That's the same thing happens with laser. We also call it laser blooming. So people like, USA built this awesome laser system. It's like, it's gonna shoot down ICBM. They fired it. It's like, wait a minute, why the heck that ICBM is not melting? Yeah, atmosphere is like, no man, you shall not pass. So flat out we have to find something that can go through atmosphere without dumping too much of its energy, and the exposure have to be around 1 hour. That's the sweet spot. So that's just the laser part. Now what about the sail? Now sail, fundamentally, because our serious weight limitation, it has to be few atom thick. At this point in time, it will be flat out transparent. Nothing is like, few atom thick and you could still able to see it. Like, it will be flat out transparent, and it has to be 100% reflective to that spectrum that is used by the laser. Thankfully we have achieved it. That's how we have laser cutting technologies. Think of it this way, like, how the heck you are reflecting a laser that is cutting a 1 inch thick steel? How the heck you are doing that? Let that sink in, that there is a mirror that is reflecting a laser that is cutting 1 inch thick steel, or sometimes even more than that, because every element has a different unique property. So if you can fine tune your laser, it's like, my laser is exactly 550 nanometer. That's it. Like, you can fine tune that puppy. You can find an element in periodic table that's like at that wavelength. That element is like, you shall reflect. You shall reflect. You will not go through me. You will just reflect. So flat out, if you found something that on a molecular level reacts properly to that wavelength, you can have absolute 100% reflectivity. We have achieved this in lab almost to 100%. It's like, 99.99. We have achieved good enough where these things won't melt, because you have to understand, you are firing hundreds of gigawatt of laser. Even with laser spread, you're talking about like so much energy dumped into a small place that if it's not reflecting 100% of it, the waste heat alone will melt this puppy, and these puppies have 1 gram in weight, so it will evaporate instantaneously. So fundamentally you have to achieve 100% reflectivity, and it has to survive thousands of G. At this point, a few atom things, graphene is there. 100% reflective, I'm pretty sure somebody could figure out some coating or some wavelength that works perfectly well with graphene. Let's say that can be done. Another aspect is, somehow it still has to be harder than diamonds, because it has to exceed hundreds of G-force. Basically G-force, when you are talking about rockets, 3G, 4G, and basically at that point human rating goes away. Like, by the time you are like, okay, it's constantly gonna be at 10G, yeah, no thanks, flat out no thanks. Some ICBM killer missiles that are made, they can achieve YOLO speeds. Basically they are made for 100 Gs of acceleration. That can be achieved. Here's the, it's very big, very heavy, and only that way they can make sure the electronic does not just poof, turn to dust. How the heck you gonna do that in 1 gram? You have to do all that while having a giant sail, while having strong enough and reflective enough that it does not gonna melt, and somehow still physically endure G-force of 1000 G, or sometimes even more than that. So yeah, flat out even more complex system. So reality is, like, when you look at the bigger picture, it does not matter whether Stephen Hawking was fond of this idea, or Carl Sagan was fond of this idea, or Neil deGrasse Tyson, or whatever have you. Neil deGrasse Tyson even made a very amazing video in his series. I have provided the link down below of Cosmos. You can see that. So reality is, you are talking about a big ass laser, and you are talking about a really big ass laser. What does that mean? That simply means it can destroy anything in space, which includes space station, which includes satellites, which includes spy satellites, which includes other orbital things that we may do, or maybe even damage something on the moon, because again, these are aimable lasers. It's not like it's fixed. It's aimable by its inherent design. Anything in its field of view can be destroyed. So fundamentally, you are talking about something that every politician is like, yeah, let's try not doing that. So flat out, right there, done, game over. Don't even think about it. Another aspect, you are talking about 100 gigawatts. Like people are talking about 100 gigawatts. It's just a 100 gigawatt laser. I'm like, dude, we don't make that kind of energy. And did we forgot as a humanity is that lasers are only 30% efficient? Best case scenario. So you are talking about like minimum 300 watts gigawatts of electrical requirement. Let's not try to figure out how the heck you're going to get that 300 gigawatts of electrical energy and how much pollution will cause just trying to get that. So fundamentally, the heat output of that system alone would be very bad for Earth. Like it will take Earth days to cool off, because Earth is not very transparent to infrared. If it was transparent to infrared, we would not have to worry about global warming, although we may be froze to death. So you get the point. So fundamentally, that wasted heat is also a big trouble that we are not thinking about. This is heat is so much that you can literally melt ice caps away. So that's that. And once you have done all that, let's say you somehow figured it out. Let's say your mathematics is like, dude, even if you fire this powerful laser, Earth will dissolve the heat in, let's say, 1 week or something like that. Let's say you figured it out, and every humanity came together and it's like, let's do this puppy and all that jazz. What are you getting at the other end? First of all, you have to launch thousands of them, and 90% of them would be destroyed. Why? By the time you're going through the Oort cloud, you are traveling at 20% light speed. Oort cloud is dust particles, lot of them, kilometers of them, hundreds and kilometers of dust cloud you have to go through. Fundamentally, you will be very lucky if 1 or 2 even made it through. So flat out, that's the biggest thing. You have to somehow do that. Let's say you did that. You have to do the same thing while you are going to Alpha Centauri. It will also have an Oort cloud of its own, which you have to punch through. Good luck trying to do that. And let's say you somehow luckily able to manage that. Somehow you have a system that is 1 gram and somehow can communicate 4 light years in radio communication. Somehow you have that. Here's the deal. You will not have the ability to slow down at the other end. How the heck you gonna slow down? You cannot. Flat out you cannot. So you're gonna give a flyby. So you're gonna have a planet and like we humans do flyby missions. All our early missions were flyby missions. Heck, even the latest Pluto mission was a flyby mission. But here's the speed at that point versus light speed, they are on a different. Light speed would be like, it would be so fast that literally the optical properties will start changing. Like realistic calculations have to be taken into picture editing sort of. Basically your Photoshop will have a, okay, this is taken at 20% light speed, so de-stretch the image. So fundamentally, even if you do all that, all you are getting is a flyby, and at that speed, at that distance, you are talking about like a 1 microsecond of exposure time for all your instrument to collect data. Yeah, no. So flat out, and we don't even have technology that even comes close to achieving this. It's like magical laser system that somehow can go through Earth's atmosphere without roasting the atmosphere, somehow making a material that is few atoms thick, less than a gram, and somehow it can withstand 1000 g-force. Flat out diamonds will crack at that kind of oomph. So fundamentally, we do not have any technology at any place in time that can even come close to be like, okay, let's maybe able to do that. Flat out no. Flat out nope. So if I have to give a rating to like 0 to 100% at this point in time, 2020, I'm giving it a 0% probably. So practically speaking, the likelihood of us seeing this project being built is 0. So this was my presentation on Starshot project. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.